Welcome to Stat Harbor Analytics. Statistics is not just a collection of formulas. It is a way of asking better questions under uncertainty. But to understand statistics deeply, we need the right mathematical language. The first language is functions and models. A model is not reality. It is an approximation of how variables relate to each other under uncertainty. When we write a function, we are asking, how can we represent a relationship? This is the foundation of regression, prediction, machine learning, and structural modeling. Then come derivatives. They help us understand local change. Derivatives help us understand local change. They answer, what happens when something changes slightly? This is why they appear in optimization, score functions, gradients, marginal effects, and influence functions. Small perturbations often reveal the structure of an estimator. Small perturbations often reveal the structure of an estimator. This is a fundamental principle. Next, we need integrals and sums. Statistics often requires aggregation. We combine many possible outcomes to define expectations, risks, probabilities, and likelihoods. Global quantities are built from many small contributions. Then comes probability, the formal language of uncertainty. Probability is the formal language of uncertainty. It allows us to define random variables, distributions, dependence, independence, conditioning, and Bayes' rule. But probability is always tied to a model. It is not uncertainty itself. It is a framework for representing uncertainty. From probability, we move to expectation. Expectation is where statistics starts targeting something. A mean, a risk, a prediction error, an average treatment effect. These are not just numbers. They are functionals of a distribution. Statistics is often about estimating these targets from data. Then we need variance and uncertainty. Variance tells us how much quantities vary. In inference, uncertainty is not a weakness. It is information about precision. Standard errors, confidence intervals, and uncertainty quantification all come from this idea. Next is likelihood and optimization. Which parameter values make the observed data most compatible with the model? Optimization gives us a disciplined way to choose estimates. This is the foundation of maximum likelihood, generalized linear models, regularization, and many estimation procedures. Then comes geometry and linear algebra. Data can be understood as vectors, spaces, projections, and distances. Least squares, orthogonality, PCA, and dimensionality reduction all rely on this geometric view. Estimation can often be seen as projection. Then we reach tangent spaces and local models. This is more advanced, but extremely powerful. It asks, what infinitesimal directions can a distribution move in? This language helps us understand influence functions, efficiency bounds, semi-parametric inference, and double robustness. Finally, we need asymptotics. Asymptotics asks what happens as sample size grows. The law of large numbers, the central limit theorem, bootstrap, and walled inference all live here. But large samples do not fix bias, poor measurement, or model misspecification. They only stabilize the estimator under assumptions. So the central statistical framework becomes clear. First, define the target, then choose an estimator, then quantify uncertainty, then make an inference. Mathematics provides the language. Statistics answers the question. And the goal is not to learn math for its own sake. The goal is to understand what your analysis is really doing. Learn it, connect it, apply it.